Hello, you absolute legends. This is a bomb calorimeter problem here. 0.562 grams of graphite combusts inside of the bomb. The temperature of the bomb increases from 26.74 to 27.93 degrees Celsius. What is the heat capacity of the bomb calorimeter? Before taking a moment to talk about how this experiment is conducted, let's think about the units of heat capacity. Because at the end of the day, our units have to line up right there. The units of heat capacity are joules per degree Celsius. So at the end of the day, we're going to need to know something about joules and something about Celsius. Well, I already can see something about Celsius in a temperature change. But the joules, the energy that is released by the combustion of graphite. Let's look at a picture of this experiment. So here's a picture of a bomb calorimeter, a cutaway. And a bomb calorimeter is a closed container where something is combusted or exploded or blown up inside. And from that explosion, energy is released into surrounding water, and that water temperature goes up. So when we see in our problem a temperature increase of a little bit of about 1 degree Celsius, that makes sense when we're talking about carbon exploding in the presence of pure oxygen. So this is how the bomb calorimeter is set up here. You put in a small amount of sample, pump it with oxygen gas, pure oxygen environment, ignite it, and then watch the temperature rise. So the joules of energy that we are going to use to calculate the heat capacity is going to come from the combustion of graphite. And the temperature, the denominator, is going to come from the change in temperature that was observed in the experiment here. Now, the combustion of graphite, how much energy was released, we can calculate that using what's called standard enthalpies. Now, standard enthalpies are numbers that are recorded and cataloged in textbooks and tables. They're not numbers that you're expected to memorize or know by heart. So the combustion of graphite, or the enthalpy calculated, the enthalpy of that combustion there, we use the products minus the reactants to calculate the total enthalpy right here. So we need our balanced chemical reaction. We're using carbon solid, and it is going to combust in the presence of pure oxygen, and it is going to form CO2 gas. We're saying this is a complete combustion here. Now, these numbers here for the products and the reactants, you Google them or look them up in the back of a textbook. Now, some of these numbers for carbon solid is 0 kilojoules per mole, and for oxygen 2 gas, it's also 0 kilojoules per mole. These numbers being 0, it seems kind of weird, but those numbers are rated at 0 because they're used to calibrate other carbon compounds or other oxygen compounds. And here's what the Google page looks like when I Google enthalpy of graphite. You can see a couple different carbon compounds show up. Graphite is given as 0, and then other carbon compounds are calculated based off graphite being 0. So CO2 happens to be on here, and it has a value of negative 393.5 kilojoules per mole. Let's write that down because that is our product in this balanced chemical reaction, CO2. So here I have my enthalpies for my product and both of my reactants. And I'm going to use this little equation right here, products minus reactants, to calculate the energy or enthalpy or joules that are to be released from this reaction here. The product is negative 393.5 kilojoules per mole. I have two reactants, so I'm going to add them together. They both just happen to be 0, so that math is pretty simple. So negative 393.5 minus 0 is just negative 393.5 kilojoules per mole. This sign of negative makes sense, and it's worthwhile to double check that, because a negative sign for enthalpy means that heat is released. We know that heat is released because the water increased in temperature. So this value and this sign here makes sense. Now, we want this answer to be in kilojoules. Excuse me, we want this to be in joules, not kilojoules per mole. We didn't have 1 mole of graphite. We had less than 1 mole of graphite. So let's use that to calculate how much energy was released when we had 0.562 grams of graphite. I do want my joules on top. So when I start my scaffold, I'm going to start that with joules on top. And this is the enthalpy of formation of the combustion of graphite to form CO2. And if we had 1 mole of graphite, or 12 grams, this would be how much energy is released. But we had much less than a mole, about 1/24th of a mole. So we're talking about graphite, carbon. Graphite is 12 grams per mole from the periodic table. Moles cancel. And we had 0.562 grams of carbon. I don't know if you can see there, but the units grams cancel out. And I do want this numerator finally in joules, so I'm going to do the conversion right here of kilojoules to joules. 1 kilojoule is 1,000 joules. With my calculator, there it is. Negative 393.5. Or by 12. So about 18,000 joules of energy was released here. We want our calorimeter, the heat capacity of our calorimeter, in the units of joules divided by degrees Celsius. So the temperature change that we see here, 26.74, increasing in temperature to 27.93, that is an increase of 1.19 degrees Celsius. And that's just from subtracting those two numbers right there. And those are the values of the energy that was released and how much the temperature increased of the calorimeter. And those are the units of heat capacity. So now all that's left to do is divide these numbers by each other. 18,363.33 divided by 1.19. Yeah. 63. And I get 431.37 joules per degree Celsius. So that is the heat capacity of the calorimeter, meaning that every time you put 15,431 joules of energy, the calorimeter is going to increase by 1 degree Celsius. This is a long, complicated problem. Please comment below if you have any questions. I hope this helps. Thank you.